Hello, it's me, Ayahuasca from Marijuana Garden.
This is a 1 in a billion experiment. In the strange and fascinating world of quantum mechanics, scientists have just achieved a monumental feat. They split a single photon. But this isn't just breaking something in two. It's a controlled division that confirms one of the most fundamental laws of the universe holds true, even for a single particle of light. The law in question is the conservation of angular momentum. In our everyday world, we see it when a spinning ice skater pulls in their arms to spin faster. It's a measure of an object's rotational motion. For decades, we've known that light beams can also carry a form of this called orbital angular momentum, or OAM, where the light twists like a corkscrew as it travels. But a critical question remained. Does this law apply to a single indivisible photon? In a landmark experiment, a team of physicists at Tampere University, alongside collaborators in Germany and India, set out to answer that question once and for all. Published in the prestigious journal Physical Review Letters, their study details how they fired a single photon with a known amount of orbital angular momentum into a specially designed nonlinear crystal. Through a process called spontaneous parametric downconversion, that one photon was converted into two new photons. The result was breathtakingly elegant. The two resulting photons had OAM values that were equal in magnitude but opposite in direction. They perfectly canceled each other out, proving that the total angular momentum was conserved, even at the quantum scale. Achieving this was an immense technical challenge. The nonlinear process is incredibly inefficient. For every billion photons they sent into the crystal, only one would successfully split in the desired way. Detecting this single, rare event required extraordinary precision and custom-built single-photon detectors, sensitive enough to register the faintest whisper of light. It was the ultimate search for a needle in a haystack. This breakthrough does more than just reinforce a cornerstone of quantum physics. The very nature of these split photons opens a door to a new generation of quantum technologies. The reason? The two photons born from the split aren't just separate particles. They show signs of being quantumly entangled. Entanglement is one of quantum mechanics' most famous phenomena, what Einstein called spooky action at a distance. It means the two photons are intrinsically linked. If you measure the twist of one, you instantly know the twist of its partner, no matter how far apart they are. This experiment provides a new way to create photons entangled by their orbital angular momentum, a property with huge potential. This has profound implications. In quantum communication, this entanglement can be used to create fundamentally secure networks, as any attempt to eavesdrop would instantly break the link and be detected. In quantum computing, using the multiple twist states of OAM could allow us to build qubits instead of qubits, vastly increasing the processing power of future computers. And in quantum sensing, these entangled pairs could lead to imaging and measurement devices with a precision we can currently only dream of. The next step for the researchers is to improve the efficiency of the process and refine their measurement strategies. Their goal is to generate even more complex quantum states, entangling multiple photons across multiple dimensions of their properties. By mastering this control over single photons, they are not just testing the limits of quantum mechanics, they are building the tools that will define the technology of tomorrow. Source: L. Kopf, R. Barros, S. Prabhakar, E. Gysi, and R. Fickler. Conservation of angular momentum on a single photon level. Physical Review Letters 2025.